In this video series, I want to boil down some topics that are traditionally only introduced in high-level optics to a level more accessible to a wider range of scientists and engineers, who may be interested in the end result, but not have the background to trudge through the math behind them. Since I don't know your background, I'll start in this video with a brief introduction to some basic optics concepts that you have to understand to move forward, and then in the next video, we'll move on to applying these in some real-life problems you might be working on. If you already have a basic understanding of light and optics, I recommend skipping this video and starting on the next one. Okay, so let's jump right into it. I'll be moving at a very high level here, so if you'd like more clarification on something, I suggest you pause the video and do some of your own reading. For practical purposes, everything you need to understand about light can be described with the following four properties, each of which I'll go into briefly. The direction in space it is traveling, its color, also known as the wavelength or the spectrum of the light, how bright it is, and its polarization. The direction that light is traveling is typically described by a ray, which you can think of as a line through space from one point to another. If we have a surface that light is going to hit, like a mirror, we're typically interested in simply the angle of the light relative to the surface. Keep this in mind for later. Next is the color of the light. We all understand this intuitively. Light's color is described by how fast it oscillates as it travels, interchangeably its wavelength or frequency. Here are some wavelengths and frequencies as light travels through air that we're all familiar with. It's as simple as, instead of calling light green, we can be more specific by calling it 500 nanometers or 530 nanometers. Keep in mind two things. The color that your eye constructs from the incoming light can sometimes be more complicated than just a single color. Your eyes see some colors because certain wavelengths are missing. Secondly, while the frequency of light is the same everywhere, its wavelength can be smaller depending on the material it is in. Don't worry too much about this. Just take away that wavelength can change if the light enters a material like glass. Third is how bright the light is. This is typically described in terms of intensity. How you choose to define light's brightness depends on your application. While it depends on the field of study, more often than not in my experience, we are more concerned with the amount of light relative to some reference amount of light than the absolute. For example, if I had a window and I was shining a beam of light through it, it could be suitable to simply say that 25% of the light is transmitted while 75% of the light is reflected. There are many different ways to describe the intensity of light from a source, such as in lumens or candela, which are popular for common light bulbs. If you really want something quantitative, in my experience, the most common way to describe a useful light source such as a laser is in terms of its average power in watts, or its irradiance, which is the power over an area, in other words, watts per meter squared. Finally, you need to appreciate that as light travels through space, it vibrates in a direction called its polarization. Light vibrates in a direction perpendicular to the direction it is traveling. It can either go, referring to this diagram, up and down, left and right, or some combination of the two. If the line is shown onto some plane, like a mirror, we give names to these two polarizations, TE being the direction along the surface of the mirror, and TM being the direction perpendicular to this. If the light is straight onto the mirror, there really isn't a distinction, and the two polarizations behave the same. However, interestingly, the way light interacts with the surface can vary drastically depending on its polarization. Light from the sun or incandescent light bulbs is referred to as unpolarized or randomly polarized, meaning that the light is some mixture of all polarizations. Light from lasers or computer screens, for example, is typically polarized. The usual teaching example for polarization is how polarized sunglasses, which only pass one polarization, can let you see into water. This is because a portion of sunlight that reflects off of water at some angles is dominated by one polarization, which then can be blocked by your sunglasses. So now that you understand the basics of what goes into light, let's look at the basics of what happens when light hits a surface like a mirror. There are two basic concepts, reflection and refraction. Reflection, which I'm sure you're familiar with, can simply be described by the law of reflection, which says that the angle of incidence is equal to the angle of reflection. It's that simple. Draw your ray of light, a line perpendicular to the surface, and the same angle on the other side of the line tells you where the reflected portion of the light will end up. Refraction is slightly more complicated, as it describes where transmitted light will end up. Snell's law describes refraction and basically says the amount that the light bends as it travels into a material depends on the type of glass that's on the other side. We describe glass, or really any material that we're interested in doing optics on, water, metals, gases, by its refractive index, N. You can think of refractive index as how similar a material behaves to air. Air has a refractive index of 1. Glass usually has a refractive index closer to 1.5. Diamonds, for example, have an even higher index closer to 2.4, meaning they bend light more when it enters. Indices can go even higher, especially for materials that interact with light outside of the visible range. So that's it. You should now understand the basics to get you started with some simple optical design. To end this video, I want to make you appreciate two things about applying these basic concepts. First, while you don't really need to understand any of the math behind this, know that the laws of reflection and refraction can be generalized for any angle and polarization by a set of equations known as Fresnel's equations, which go further to describe as well how much the brightness or intensity of light is transmitted or reflected at an interface. These equations, albeit slightly more complex than our simple laws of reflection and refraction, give a surprisingly accurate prediction of the truly extremely complex interactions between light and matter. Finally, it's simple enough to study this basic problem of light traveling from air into glass, but what about something like this? This is oil and water, which we've all seen on the ground of a parking lot. All of these complex colors have to be described by applying refraction and reflection to this simple interface and accounting for small variations in thickness. You also might have encountered two mirrors being back to back, say in your bathroom. They create this interesting infinity effect, which can be accurately solved simply by repeated application of reflection and refraction. It becomes apparent then that this is a problem we can easily appreciate and is one that needs a more expedient route of solving than simply calculating angles. In the next video in this series, we'll be applying these concepts to study some real-world problems. Thanks for watching.